Welcome back to our Applied Statistics course. We're going to look at Chapter 9 of the ISLR textbook, which is, as you can see, about support vector machines. It's a common topic in introductory machine learning. And next week, we will finish off the textbook with their Chapter 10 on machine learning. Overall, recall that what we're trying to do is take large data sets and make predictions. And today we'll look at this notion of support vector machines when working with several numerical variables. And kind of thinking this a little bit more geometrically. Let me save this as something else just so I don't accidentally ruin my template file. Little bit of R history. This E1071 package, I believe, was simply a bunch of functions written by various university professors, but the functions were so useful that they keep it around. In fact, I just checked right now. The package was last updated 8 days ago. So they do maintain this package. ISLR for some data sets that we might look at today, and we'll also briefly look at ROC groups. Last week, someone in the chat made a good point that if we were looking at the 2x2 contingency tables and doing a basic arithmetic calculation for finding the accuracy, well, we might as well just have a function that does that. So I went ahead and wrote that and placed that at the top of my notes. The main part of the function is simply this fraction here. The rest is to make the code a little bit more readable. And also the textbook authors supplied a function that will produce the ROC plots. As always, if you have any questions, feel free to ask in the Twitch chat. I'll answer as well as I can. Alright, a lot of the first few sections is just to refresh your memory about what you read about in the chapter, which I guess was true of the previous labs as well. Here we can see we're pulling two columns, each with 20 random numbers from the normal distribution. They are labeled, half of them are labeled -1, half of them are labeled +1. And the hope is that this slightly strange line of code will take half of the dots and move them up by 1 unit. There may be an issue where even with set seed, we might get slightly different results than the textbook, at least based on what we saw last week. Let me bring this in a bit. Actually, maybe what I could do is put the picture in the bottom right for us for now. Like so. Okay. So at first, What we were hoping for, at least in an earlier example, is for a linear separation. If we were hoping there was a way to simply draw a straight line in between all the blue and red dots. Folks, in the conversation in chat is correct. At least for the image I have on my screen, there is no way that you could draw a straight line that will go completely in between the red and blue dots. And then you're correct. As you probably read in the chapter or heard about before, it turns out not to be a big deal if a few dots are misclassified. So yeah, you're correct. We're actually going to still think about situations where we are allowed to misclassify or have dots on the wrong side of the border. For those of you new to R programming, and for many people who use R programming, we haven't used factors much, but suffice to say, the reason why that's here is because we need it for the next line of code. And we call that classification is making usually a binary choice, like a yes or no, or if a stock's going to rise or fall, or something like that. Whereas in regression, we sought out numerical predictions. And partly because we're going after a classification problem, again, we have a conversion to factor here. We see what we're plugging into the support vector machine function. We're going to try to explain the y values, which are blue and red actually in the picture, explained by everything else, which is x1, x2. We're going to, at the moment, still try to draw a straight line to separate the blue and red dots. And as you saw in the reading of the chapter, what this cost function does is kind of like some leeway, some epsilon leeway that says how many, loosely speaking, how many dots we're allowing to be on the wrong side of the border. Once again, I lament but haven't necessarily upgraded from code that's about 8 years old. Here we see a situation where we're trying to separate the round circles from the x's, and we have a straight line border that separates the region into two partitions. So I'll explain a little bit more for the next couple lines of code. But for now, I just want to point out that we happen to plug in a value of 10 for the cost function. Index this the support vectors. I'm going to use the word nearby, but loosely, so I put that in quotes. So at the moment, I believe we had 7 support vectors, something like that. Okay, like in other modeling procedures we've done, such as linear regression, other types of regression, and the tree models we were looking at last week, the folks who make these programs for the R environment, or the R ecosphere, if you will, they like to make it so we could apply the base summary command on this. So in other words, there were 7 support vectors. If we had a different amount for the cost, we might have a different amount of support vectors. roughly put, what that means in the image is that the support vectors are the data points, regardless of x's or o's, that are closest to that diagonal border. So now what we're going to do is try out that process again, run our setup in the support or the SVM function, this time with a smaller cost, see if that affects things. We could also think of cost as tolerance in this setting. And this may be doing a better job. I should have double checked all my synonyms. Not sure if border's the word I want to say. Yeah, that's fine for now. Okay. Let's see, I'm gonna spend a couple minutes here, but to answer the questions in chat. Okay, so back to the topic at hand. Support vectors. In the picture, those are the data points, the X's and O's, that are kind of pulling on the border, on the separating border. And that, based on some theory that the book and I are not going to explain, the far away dots have virtually no effect on the separating border at all, if none. So you do not have to worry about outliers as much. But if you have more support vectors, if you have more data pulling on the border, then any additional data point is likely to move that border a lot. So the point is, if you have lower cost, it's usually better separation of the training data. And we've heard a lot of these words before. Now, what will happen in the mathematical background of all this, higher cost usually meant better adaptation later to testing data, where the separation border is not going to move quite as big. So that's that bias variance trade-off that Harish was mentioning early in the semester. So that's kind of the issue going on here. And kind of similar to various procedures we did in previous weeks, you would think there'd be an ad hoc approach. We're going to try out a bunch of different values for cost and then see what works best. Well, fortunately for us, the people who made the SVM functions decided just to save us a little bit of work. You could plug in a bunch of various values for cost, and rather than having to make separate graphs such as a scree plot, which we might see next week, or various like plots of cross-validation errors or whatnot, they already do some of that internally in the background. So after running several different values of cost, we have a quick list of the errors, and like usual, we want the smallest error. So the tune function helped us do all that without having to make all these intermediate graphs along the way and visualizing the error. And furthermore, we do not even need to keep track of which cost value was best out of the ones that we tried to plug in. Notice that we could simply extract the best model from the previous code chunk and go ahead and go into the summary of the best model. Talking about course enrollment and all that. Yeah, I was a math major at my university, so we never we math majors did not have any issues finding classes or whatnot. Worst case scenario, I would just have to go up to the professor and say, "Hey, I need this class. You mind if I just sit in for a couple weeks?" It tend to work out. But that's a whole generation ago, and academia just kind of is horrible to you you folks for many economic reasons. So, okay, to conclude that section of code so far, it was all to take the bias variance trade off into account, and fortunately, the people who made the SVM functions made a very quick way to bust through that. Alright, so the next chunk of code is now taking the the best model from the previous work on the SVM functions and trying to apply that to a slightly different set of data. At the end, we're building a 2 by 2 consistency table because the labels are simply the numbers -1 and +1. There are two possible labels. The predictions use the same label, so 2 by 2, 4 elements. What I added compared to the textbook code, I just simply shoved that table into our self-made accuracy function to save us a little bit of typing overall. But it's the same as before. We're taking the diagonal elements, the 17 that we get here, divided by the 20 data points in total. So as our custom function dictates, at the moment our model's accuracy is 85%. And make sure we understand this is on the testing data. Next chunk of code, notice that the cost is lower. While it might feel good at first to perfectly classify the data at the beginning in the training stage, we could see that the situation did not adapt well or generalize well to the testing data. And in fact, the prediction accuracy went down. I work with Professor Suzanne Cindy in a different class, and I posted something in the discussion board, and she responded with profanity. Great. Okay, let's see what this does. Suzanne had a 5-hour meeting this morning because she's helping out with something in the school. She is frustrating as heck. Oh, jeez. All right, so we have another set of data that. Funny thing is, on my computer, we probably could separate this pretty well as a straight line, but that's not what the textbook wanted. Let's see, where am I? Okay. Alright, so in this example, trying out a large cost function, seeing what happens. Like so. Maybe I'll reword this. Like so. Okay. My picture should have more X's than O's on it. That's so weird. And then finally, one more. Parlay was the cost function of 1, or cost value of 1. Referring to some of the messages I see in chat, those are all good answers. Different opinions, different varieties, different feelings, all completely understandable. I actually applied to UC Merced because at the time I did not take the GRE subject test and UC Merced did not require it. But I'm very happy here. Not for everyone though. For example, like if you wanted to study astrophysics and UC Merced doesn't offer that that type of deal. I sometimes mess up the technology every once in a while. Can I just get a quick confirmation if you can hear my voice in Twitch chat? Okay, thank you. Makes sense. Alright, so now we're moving on to the actual support vector machine. I was trying to stay away from those words earlier. Like what we did with regression, we do not have to restrict ourselves to straight lines. You could think of polynomials, and what we'll settle on are actually circles. Okay, I think Professor Suzanne Cindy is almost done cussing by now. So here we have a region in fabricated data that is much harder to separate, at least would be very difficult to separate with a straight line. And, I mean, you're all advanced students. I could use the word hyperplane. I was using the word border earlier because I was being basic. This fabricated data is virtually impossible to separate with a linear hyperplane, with a straight line. So, we tell ourselves, well, let's stop using straight lines then. Just to somewhat explain what's going on mathematically, because it wasn't obvious. What we mean by radial kernel is we're trying to kind of use this oddly shaped paintbrush. And if you ever painted, you realize that sometimes you want a really small paintbrush, sometimes you want a really large paintbrush. And the kernel is the shape of your paintbrush. So when we say a radial kernel, according to the formulation in the textbook, we're using a Gaussian shape, which you're familiar with for this 3D graph as the MATLAB logo. This is your Gaussian over a 2D surface. And what we then mean by gamma is, loosely speaking, like how steep the slope is, how quickly the Gaussian goes to zero. So sometimes you want that to be gradual, sometimes you want that to be a really steep decline. But again, when you hear about Gaussians, you could think of the MATLAB logo. Okay, so let's see what we get from the summary. Whew. There is a possibility I might have the words bias and variance mixed up. You know, it's late. But at the moment, having many support vectors is not necessarily a good thing. For the folks whose lab are not loading, I sincerely thank you for being here anyways. If you need to, just play back the YouTube video later on like double speed. In which case I'll have a chipmunk voice. Alright, so we can do this. So here in this current image, they tried to separate the values using a very large paintbrush. Yeah, that's the nice thing about you all, the math majors, CSC majors, having such a large background in math. If you ever need to pick up anything in the future, it's so easy. Like, I once took an online class, linear algebra, but computer-based linear algebra. I took it online with a professor at Brown University, but since I already understood all the linear algebra, I only had to learn the computer side. It was so easy. At least much easier for me than a lot of other students in the class. Okay, so now we have two parameters to play around with. The the cost function, just kind of like the tolerance of how many dots you're allowed to misclassify in the end, loosely speaking, and the gamma, loosely speaking, how large the paintbrush will be. And at first you'd think, well, you have to try out a bunch of different values for gamma, a bunch of different values for cost. But lo and behold, the folks who made the R functions decided to help us out with a tune function to take care of a lot of the dirty work for us. we're going to plug in 1, 2, 3, 4, 5 values of cos, 1, 2, 3, 4, 5 values of gamma, 25 um, different permutations here, fewer combinations. Oops, my roommate's DoorDash is here. And we'll see that there appears to be a global minimum. Oops, I should have kept that in mind. So at least for these 25 permutations, we could figure out the cos and gamma values with a couple lines of code. Building the contingency table as usual, we have our helper function. Spitting out the model's accuracy, we get 89%. Or in other words, only 11% of the data were misclassified. Okay. I love that RStudio has a spell checker. I think we'll just try to speed through the rest. So with ROC curves, if you haven't heard ROC, radio operator characteristics, the name dates back to World War II. What you're looking at is actually the area under the curve, a UC, which, as a side note, when you follow politics, there's a different initials for something called AOC, and it kind of reminds me of AUC. Anywho. You want the classification to get closer to as close to 100% as possible. admittedly just paraphrasing the textbook here. For the folks in chat who are getting different graphs than I am, I fully admit I have no idea why. That we're using the same code and the same data. Sorry about that. Alright, so it turns out the ROC curve switched order once we moved on to the testing data. And that's what we're more concerned about, or more concerned with. Alright, so far we've been dealing with binary classification, just two possibilities for the final result. We might want to generalize to multiple classes, multiple labels. So now you can see in my picture, green dots, black dots, and red dots, so three different labels. In our first go, let's use code that we tried earlier in the session. We'll use a radial kernel, maybe a cost of 10, a gamma of 1. And might, so far. I'm going to say this almost like a meme. There was an attempt. The textbook actually stopped there. For those of you who are considering taking Bio 175, it's a biostatistics class, and I'm actually looking forward. I'm always looking forward to it. One of the reasons, because now that I've TA'd for this class, I have a better knowledge of what we can do. And as you can see here, this example that the textbook authors do uh, is in the biology field. Also, I'm in current discussions in the biology department to what we call team teach the class with Dr. Dave Ardell, who's one of our campus experts in bioinformatics. So you'll get to hear from him as well. Alright, so the Khan dataset has some X and Y values for testing and training. Keep in mind, in some studies, especially when you're dealing with biology or humanities, when you have, say, human subjects or whatnot, it is not uncommon to have very small data sets. For example, if you're conducting experiments where you need volunteers, you're not going to be able to find or pay that many volunteers. So these numbers are smaller than some data sets we've seen in the past. I'm pretty weak on the biology side, even though I actually work in the biology department. So there are times when I might not be explaining these correctly, but take that with a grain of salt. These calculations imply that the Khan dataset is working with 4 cancer subtypes. Yeah, it's sometimes frustrating with working with the biology majors. Nearly every single question I got in office hours was, "Did I meet the bare minimum?" I was just so frustrated. I actually started just deleting some questions in Discord. Okay, so what are we doing here? Most the rest of this lab is simply an application of the previous codes. Yeah, you have a point there, Jake and Lettuce Tomato. when I was teaching Math 32 last summer, I got an angry email from a student who was like, I majored in mechanical engineering, so I never have to do computer science, never have to do computer programming. It's like, oh, buddy, have we got some news for you? I mean, he did not luck out. There was one student who would have been happier taking, or several students, but one of several students who would have been happier taking hike from Math 32. So we could see in the second to last code block that the support vector machine classified all the training data correctly. Moving on to the testing set. 1, 2, 3, 4, 2. So on a real world biology data set, the support vector machine misclassified only 2 instances. Seems pretty good. Alright, that actually brings us to the end. I know some of you were able to follow along, some of you were understandably not able to follow along. As usual, mostly because I'm not going to grade this tomorrow anyways, you have until tomorrow at midnight to similarly annotate the lab, turn it in, and whatnot. If you have any questions about the course, please continue asking them in Discord. Discord allows private messages as well. And as usual, I'll stick around for a few more minutes if there are any more questions. Otherwise, it's been good hanging out with you. And yeah, hang in there.